You are watching Part 8 of Unit 2 of Quick Precalculus Review for Calculus. In Part 7 of Unit 2, we introduced the idea of the number e, which comes up in a very natural way in terms of compound interest problems. E is a very special irrational number in math, just like pi is a special irrational number. We use this computer program that you see here, Mathematica, to both estimate and see that e could be thought of as what's called a limit. We're going to be more precise in this video. We're going to really introduce the idea of a limit and limit notation to help us ultimately define e as a limit. Limits are pretty challenging though. This is just going to be an introduction to the idea of a limit. But limits are very foundational, very of paramount importance for calculus. Limits and theorems related to limits really are what separate calculus from just plain algebra and give calculus much more power than just plain algebra. Pretty soon, not in this video, but pretty soon, we're also going to talk about alternative representations of exponential functions and inverse of exponential functions called logarithmic functions. But in this video, we're focused on limits. Here's the example we were thinking about. Finding and comparing annual percentage yields, APYs, for two bank accounts. What is the APY? It is the actual annual percent of growth. When you've got a compound interest problem where R is the nominal annual interest rate and N is the number of compounding periods, you can use this formula, this expression right here, to find the actual annual percent growth called the APY. I also related the APY to what I called B. B was the annual growth factor based on a certain number of compounding periods per year, N. It was a function of N. Since APY was B minus 1, you can also say B is 1 plus the APY. We used Mathematica to make some graphs, and we also looked at the value of the B, 1 plus 1 over n to the n power, when R was this great interest rate of 1 or 100%. And we observed that the value of B kept getting larger and larger as n got larger and larger, but with sort of diminishing returns. We never got past about 2.71828. So there was some limiting process going on there. That's what we're seeing. In fact, as n gets bigger and bigger, the value of this b is getting closer and closer to the special number e, which we can enter in Mathematica this way to see the first 1,000 decimal places, including the 2, and compare these numbers to see that this limiting process seems to be true. We also saw that we can actually change the value of r and still relate it to e. If I make r equal to 10% or 1/10, the value of b doesn't approach e anymore, but it's still related to the number e. It's in fact e to the 1/10 power. The 10th root of e is what this value for b is approaching as n gets larger and larger. Right? So let's be more precise. Let's try to describe first of all what we are observing here. What are we observing here? We are observing that the value of 1 plus the APY, which is b, the annual growth factor, which equals 1 plus r over n to the n power, gets what? Gets closer and closer, as close as we like, you might say, to what? To the value of e raised to the r power, which when r is 1 is going to be e to the first power, or just the number e. As n, the number of compounding periods, gets larger and larger, you might say without bound, to be a bit more precise. Okay? That's what we are observing. The value of this thing, 1 plus r over n to the n power, the b, gets closer and closer to e to the r as n gets larger and larger. Here's the special notation. We write, here's limit notation. Anytime you see an LIM by itself in math, it almost always means limit. It's a limit of what? A limit as n goes to infinity, and here's the way you write n goes to infinity. You write an arrow, n arrow infinity. What does that mean? Okay, infinity is not a number. Okay, this is just special notation, convenient notation to indicate that n is growing larger and larger without bound. It's getting past any given number eventually. Of course, this is all in your mind. You're all just imagining all this. It's suggestive language for your imagination. It's not still quite precise math yet. Okay, in calculus, you've got your precise math and you've got your imagination, your intuition. Both are important. You want to develop both. The precision is harder to develop actually, but they're both important. What would we write here? We would write that the limit as n goes to infinity of 1 plus r over n to the n power, that equals e to the r power. And the limit symbol is essential. I'm not saying 1 plus r over n to the n power eventually equals e to the r. That's not what I'm saying. I'm saying the limiting value of this quantity equals e to the r. Thus, this limit sign must be there. Okay? That's one way to write it. There are some other ways to write it, but this is one way to write it. Let's go ahead and boldface this and make it blue. This also means that, well, if we copy and paste this whole thing over here, if I replace r with 1 to get e, that this limit is also true. I don't know why I lost the boldface in blue there. Sometimes it stays, sometimes it doesn't. Okay, so this is really a definition of the number e as a limit. Okay, right here. That's a fundamental thing to know. If you're a math major, this is something you should know for the rest of your life. You should know that e can be defined this way. Alright, let's spend the rest of this video, the last few minutes here, trying to get a bit more precise about this. I'm going to introduce a new function. I'm going to call e of n, where this e is a lowercase e, so that's not representing the number e, but it's suggestive of the number e, to equal b, really. 1 plus 1 over n to the n power, where I am taking r to be 100%. I could do other values of r as well, but we'll just keep it simple and take the r to be 100%. By the way, Mathematica does have a built-in limit command. Limit en, comma, n arrow infinity. Actually, I can just do that as a... Yeah, there we go. The limit of this is the special number e. There it is. I don't know if you can tell, that's sort of a special looking e. It's got an extra line in it there. Mathematica calculated that limit. Alright, so that's going to be the value of b for different n's. What I want to illustrate is how this idea of how I can make this expression for b as close as I like to e as n gets larger and larger without bound. So I'm going to use capital N again, and I'm going to use the absolute value function, which in Mathematica is ABS. The absolute value of the difference of two numbers is the distance between them. I'll say that again, that's a very important thing. You might want to write it down. The absolute value of the difference of two numbers is the distance between them. So the absolute value of e of n minus the number e is representing the distance between them. I want to estimate this to, say, 20 decimal places for different values of little n. Let's go ahead and plug in different values of little n, like 1 first, for example. The distance is about 0.7, which should make sense. When you plug in 1 here, you get 2 to the first power, which is 2. 2 minus e is negative 0.718, approximately, so the absolute value is approximately positive 0.718. If you plug in n equals 2, it gets smaller. You plug in n equals 3, it gets smaller. The distance between these things keeps getting smaller and smaller. Can I make that distance less than 0.1, for example? Yes, by taking n sufficiently large, maybe 10 will work. Nope, doesn't quite work. Let's try 12. Not quite. Try 13. There we go. 13 is the first value of n that makes the distance less than 0.1. How about 0.01? 1/100th. Try n is 20. Nope. Try n is 50. Not quite. Try n is 70. Try n is 100. We're getting diminishing returns here. Try 200. There, that's less than 0.01. Try 150. See if we can find the first one that works. That works just barely. Try 140, 130. Okay, somewhere between 130 and 140 is going to be the first value of n. Maybe it's that. Yeah, 135. That's the first value of n where the distance is less than 0.01, etc. By taking n sufficiently large, I can make this distance as small as I like. If n is 100,000, then the distance is almost less than 0.00001. Okay? Actually, I think that this can come out in scientific notation as well if you make n big enough, although it probably takes too long if I make n too big. That's a good lesson for me here. Let me abort that evaluation. Let's go down to 1,000,000 instead of 100 million. I think this, yeah, there we go. And it's in scientific notation. about 1.36 times 10 to the negative 6. So that's my introduction to the idea of a limit in the context of e. We'll probably talk about this a little bit more, think about it graphically in the next video, but then we want to get back to thinking about exponential functions and ultimately logarithmic functions.